Welcome back to the shrine. If you're here first time, I need to tell you I've been working on an engine development for the past 20 years. I'm at the stage where I am making parts for the engine. This place is called the Shrine for the hand-me-downs of the industry, referring to the machinery of a bygone era that I keep running. As you might have noticed, I've been doing bi-weekly updates. If you guys need more, I've been posting a lot of short videos on my YouTube channel and on my Instagram. See the links below. So the first component I've been working on is a tappet or a lifter for my engine. And I looked up today the origin of the word tappet. It goes back to the late 1700s, and it is basically just tapping on something with the wrong spelling. That's all it is. I tried to see if I can use parts from some other engines, but none of them will fit my application, so that's why I'm making these tappets from scratch. If you're interested, there is a bunch of videos on my channel, from forging the tappets to machining it, the upper side, the lower side. And today we finally got to the stage where the last machining operation is being done, which is drilling a cross hole from one side to the other side through the center. That is gonna be the lubrication hole. That's where the oil is gonna go into the tappet. So the oil is gonna go in either this side or that side, depending on how this is being installed in the engine. It's a symmetrical part. And on one side, the oil is gonna lubricate the push rod joint. And then on the other side, it is gonna trickle down into this pocket here, where it's going to lubricate the roller. So there's going to be a roller and a bearing in this area. Here is the tappet drawing, and you can see the through hole right here. So it's a 2mm through hole. Don't trust my print, I updated it. So it's a 2mm through hole, and it goes from one end to the other. So you can see the diameter of the tappet is 21mm. So the size of the hole is 2mm, and then it goes 21mm long. So this operation presents its own challenges to make 10 parts for the engine that will be identical. And so in order to facilitate this, I came up with a fixture that I will be able to use on a CNC and basically do the drilling operation. Now, the first cut looked like this, and the idea was that I'm gonna have a part here machined that has a register diameter that's the same size as this hole. This can be placed on that part, and then later on I'm gonna put a plate here to orient this. And later on I came up with this design here. So again, repeatability was my main goal, and also I wanted to make sure that I minimize the chances of tool breakage. Drilling this 2mm hole is a hefty task. One of the issues is that this central hole here is already drilled. So you can see there's a hole inside that's drilled. So when the drill is coming through, it is gonna meet this hole first, and then it has to go through and penetrate, the entire thickness of the stock. This part was machined mostly in a collet chuck using the 5C collet. Now for this operation, I cannot use the collet chuck because of constraining it. So the hole is right in the center. This part is 30mm long, so about 1.1 inch. So if I want to come down and drill this hole, the drill chuck is gonna bump into the collet fixture. Otherwise, I have to use a real long drill to come in and then drill completely through. So because of all these reasons, I came up with this vice design. So this tool took about 20 hours to design, write the G-code, machine the various parts, and basically put it together. And I know that because I've been logging my hours for the last 8 years. That's related, you know, to this engine project. Again, this was the first iteration, and you can see it's fairly similar. The difference here is that it's open on the sides, and then this one has the pocket. But I thought since I have the machine, I might as well use it properly and create this tool. So the way this tool works is I have a knob here and a screw that will tighten this spacer against the tappet. So you can see I can take the tappet out, and then there is a little part here that initially I wanted to machine on the lathe first, but then again I thought I have a CNC, so I might as well machine this on a CNC. It's a simple little part. So what I've done first is I drilled the 3 holes. I reamed the side ones to accept 5mm pins, and then the center one is threaded to M8 size. This size here is designed to accept the tappet with a little bit of gap. Obviously these parts have variations between the different parts, so I didn't want to have a tight fit. And then this large part has the same type of holes, so 2 5mm holes reamed, and then the center one is just clearance for the M8 screw. So once I install this, you can see it's got a real nice fit. There's no weeble wobble on this guy. So when this part was machined, it was facing up, and then there was a projection down here held in a vise. So once I machined it, I flipped it over and I decked it. And there was about 80 microns difference between these two sides. So what I ended up doing is I set it up on the surface grinder, and then I ground this surface. You can see it's not perfect. There's some discoloration because I don't use coolant on the grinder, and I was probably going a little aggressive on it. But nonetheless, it's a nice part. So how nice it is. This side is 1127, and then this side is 1127. So that's good for the girls I go with. So there's 6 degrees of constraint that I need to get rid of. So this pilot diameter is going to take care of the X and Y movement. Okay, so it cannot move this way, it cannot move left or up and down. And then this pocket here is going to make sure that it does not rotate. So there's a little bit of wiggle, but again, there's variation between the parts, so I need to maintain a certain amount of gap. So here's another part. You can see it goes in. Now the gap here is going to vary because some of these parts, again, are not fully grown. So here's a third one. You can see it fits nicely. It's got a little bit of wobble. And then this part is made out of brass, so not to mar the surface. I tighten up this knob and it's not going anywhere. So the way the fixture is designed, you can see that down on the bottom here it's got 2 cuts, one on each side. So when I put it in a mill vise and I tighten the vise, I don't need to use parallels underneath. And so it's going to grab on this bottom surface, which is about 6mm deep, and this guy is constrained. So every time I put in a new tappet, that hole is always going to be in the same position. So here's some footage of the manufacturing of the parts. Especially this part here, when the pocket was cut, I really enjoyed that part. The machine was just running flawlessly, and that 1/4 inch end mill was just hogging out this mystery metal like there was no tomorrow. One thing I'm really proud of, that I didn't break a tool and I didn't crash the machine. I also got a new tool. This is a thing of a beauty. If you guys don't have one at home, you should buy one. This is a Noga internal deburring tool, and it has this deburring blade at the tip, and then it's got a button on the end. So when you're inserting into the hole, you can press this button and it will straighten it out. So you can imagine that deburring these holes from the outside is really easy job, but from the inside there's no way to really get in there with a deburring tool. So that's why this Noga tool is designed to do. So you can insert it, come back in, and then just casually turn it, and then it's gonna get rid of the burrs. So now the task is basically to set this up in a machine, find the 0 coordinates, use a G81 cycle to come in and center drill, because what we are doing is we are drilling on a cylindrical surface. So if I use just a normal jobber drill bit, it can slip off and then break ultimately. So what I want to do is do a pilot hole, a little center drill, and then change the tool and then come in with a 2mm drill and finish the drilling with a G83 PEC drilling cycle. So to do that, I got a couple new drill bits here. So these are 2mm in diameter, bronze oxide finish for her pleasure, super sharp, brand new. So I'm hoping for the best with these drill bits. So that was 44 seconds of terror on this carbide welding machine. I'd say this little fixture worked out pretty well considering the circumstances. There's 10 good parts here. You might ask, where is number 11? We had 11 before. Well, yeah, you know what happened. So this is what I was afraid of. This little drill is coming down on a business end of a CNC machine. doesn't have really fighting chance if something goes wrong. What happened in this case, I think, is the following. So because the tool changer is not working, I decided to install the center drill and then come in and center drill the hole, and basically have the same setup and just swap out the parts, what I've done before. Now after all this was done, then I put in the 2mm drill and I started drilling the parts. I think what happened is some of these parts, you know, at least this one, was not seated properly. So it wasn't in a proper position for whatever reason. There might have been a chip adhered here. I don't know, something happened. But when this drill came in, it was off. It wasn't off by much. It might have been 0.5 millimeter. But when the drill is going through and it's completely, you know, kind of submerged, the cutting part or the flutes completely submerged in the part, you know, then you're gonna have shear and bending on this little drill, and that's why it's broke. You can see the remaining of the drill is still in the part, so that is technically a scrap. You know, that's why I was so careful to design this step. Another thing I found is I use both of my drill chucks. So you can see this one has a Cat 40 taper, and it's just one of those, you know, hand tightening chucks. Here's the other one. It still has the drill installed. They both had about 150, 180 microns of runout right here. So these chucks are not holding the drill precisely. So 150 microns is not much when you are using a 8mm drill. But when you are using a 2mm drill, that is 10% of the diameter. That is significant. So for the production parts, I need to get my big boy chucks, something that has a higher precision than these. So I got plenty of other chucks that I can use. Like this one, I can put this in a 1/2 inch collet and see how much runout it's gonna give. This is a Jacobs number 2, and it says right here, made in United States of America. It's in Connecticut, Hartford, Connecticut. Doesn't get any better than that. So as you can see, all the holes are drilled through. Got one of the parts set up in the optical comparator. Just using this V-block. This is what it looks like on the picture. So the light is passing through right in the center. So one division here is 10 thou. So there's 1, 2, 3, 4 divisions. So that would be 40 thou, about 1 millimeter, and that is the radius. So the diameter is around 2 millimeters. I got one of these drills. We're gonna go and insert into the hole. So once I insert that 2mm drill, this is what we can see. So you can see if I wiggle it a little bit, we're gonna have some light coming through right there. But based on the divisions here, it's about 1/2 division. So 1/2 division would be 0.1 millimeters. So that means that the hole is sort of nice and centered. It's about 0.1 millimeters off. It's basically larger than the drill bit. Let's go and plug in a different one. So I'm going to take this one out. Find another random one. Plug this in. Adjust the focus. Again, you can see on this one it's got the proper hole size, so 4 divisions. That's the radius. And then once I insert the drill, you can see a little larger crescent there, but it's still in a range of, I'd say, 0.1 millimeters, maybe 0.15. So if I hear any complaint from the oil that it cannot pass through there, I'll let you guys know. I put it in the comments. Optical comparator is your friend. Let's look at the dimension from the edge. So the center should be 12 millimeters. It's a 2 millimeter drill. So this size should be around 11 millimeters. So 10.61 on one side, 10.4 on the other side. So 2/10 of a millimeter. I'd say that's sort of acceptable. This is not the right way to measure that hole, but just wanted to show you it shows 197. So let's look at another one. This one is 10.84 on one side, 10.98, 96 on the other side. So it's a tenth. It's a tenth this way. Okay, so the drill went about 1/10 of a millimeter. Migrated 1/10 of a millimeter on 21 millimeters length. I did cut a chamfer on the other side, so as far as it goes it's smooth, but after heat treatment these surfaces will be ground. Otherwise it's looking like something. It's looking like a tappet. As far as the machining, I need to make sure that when this guy is installed and I come in with the center drill, I will be able to change the center drill out to a drill in the same position of the part. I should be able to come in and drill the final hole. As far as the feed and speeds, I was using around 2500 RPM for drilling and 125 millimeters per minute feed rate, so that would be 5 inches per minute feed rate. But after I broke the tool, I basically cut it in half. So I finished the rest of the parts with 60 millimeters per minute feed rate, and I left that 2500 RPM unchanged. So this is going to be a wrap for today. I appreciate your time. I hope you enjoyed the video. Let me know your thoughts in the comments below, and don't forget to subscribe to see what I work on next. See you next time. Bye.